Today we will be continuing with what we were discussing in the first lecture, and after that we will be going to the sheet deformation processes, the basic fundamentals of sheet deformation processes. So, the effect of properties on forming behavior of the metal, especially in sheet metal, is there. Let us look at what are these properties which affect the forming behavior of metals or metallic sheets. So, some of them are the shape of the true stress strain curve. So, from the true stress strain curve, how we will have an idea how the material will behave. The anisotropic property of the material of the sheet, because that also in a way depends upon the processing history of the material. Then what is the fracture behavior, of course, that we cannot have any control on that, but at least we will know how it takes place. And it is very difficult to have an idea about the fracture in sheet metal forming operation. Only thing is, as a priori we will be having the knowledge about it, but still we will have an idea where the fracture is going to take place. Then the homogeneity of the material, the surface defects, the damage at the microstructural level, rate sensitivity of the material or the workpiece material, and the mechanical test we are doing it. What are the other tests which is possible also we will have to see. So, first let us discuss about it one by one. First is the shape of the true stress strain curve. The factors which affect the forming behavior of metals are mainly the strain hardening, the yield strength, and the elastic modulus. If you look at the stress strain curve, you will have an idea, like suppose it is like this. Okay. So, if this is your yield strength, and this is your ultimate tensile strength, this is your fracture point, this is your Young's modulus value of the material. So, from here to here, the material is the work hardening region. This is the uniform deformation region, and from this point to here, so from the yield point to the ultimate tensile strength, how much stress increase is possible, okay, and what is the strain during that period. So, this gives an idea about the thing, and so if the strain hardening is high, the formability generally is found to be better. Why? The strain hardening, if it is high, there will be adequate stretching and uniform distribution of the strain. So, you will find that the thinning effect will get reduced with the material having higher work hardening rate. Of course, your stress increase will be very high, okay, for plastic deformation keeps on increasing, but material with a higher work hardening rate will give you more elongation also, mainly because the thinning effect is reduced. Now, the high ultimate tensile to yield strength ratio, so this to this ratio, that also will help in, so that gives is an indicator of the work hardening rate or strain hardening. Okay. Then total elongation, how much you are going to get before the material fails, that is also, if the elongation is very large, then your forming behavior will be better. Okay. So, that means because you are having a higher uniform elongation, and these are all indicators of higher work hardening or strain hardening. Now, high yield strength is required mainly for lightweight application, because with the advent of the new material, where people are just looking at lightweight application, that means high strength to weight ratio materials, especially that is where the light metals like aluminum and magnesia alloys are coming into picture, or titanium also to some extent is coming into picture. Because with a lighter the material, for a specific output if you want, you need to have only very small weight of the material, that means the efficiency can be increased. Okay. So, that is why the high yield strength material is required, and for the same material, forming is difficult when the yield strength is increased. So, if you are by some means, so if you have a one material, you can do some thermomechanical treatment, and for thermomechanical treatment you can either increase the strength or decrease the strength. So, your yield strength, if you increase it by some thermomechanical treatment, naturally your yield strength will get reduced, that is all. So, for forming, it is better to have say reduce the yield strength and after the deformation process you do some heat treatment so that your yield strength is increased. That is the best advantage of doing it. Okay. So, it is difficult. So, when the yield strength is increased, other properties like toughness and ductility will get reduced. So, that will be adversely affected. So, that one has to be careful about it. So, from the point of if you have a higher capacity machine, then it is better to have deform the material in the higher yield strength value. Okay, but if your this is capacity of the machine is less, then you have no other alternative than to give heat treatment and reduce the yield strength. And high elastic modulus is desirable as it will give a stiff component. So, lower modulus have high spring back effect and difficult to control the dimension. So, with any material with a lower Young's modulus value, stiffness value, it is very difficult to control the dimensions. Okay, but with a higher one, though you may need to have higher stresses, but you can control the dimensions properly. And another is that high yield strength to Young's modulus value ratio will have higher spring back. That is also people have been experimentally they have found that those materials having high yield strength to Young's modulus value ratio, they have a higher spring back effect. Now, certain things is the anisotropy which we were discussing earlier. If the magnitude of anisotropy is greater than unity, then width strain is larger than the thickness strain. So, anisotropy is the ratio of width strain to the thickness ratio. So, if the higher the value, width strain is larger. So, it also represents greater strength in through thickness directions. So, any material with a higher R value, you will see that its higher strength is there in the through thickness direction. Thereby, due to that, your thinning is reduced. So, so local necking and then fracture. That part will be reduced. You can have a higher amount of strain for that. High value of normal anisotropy favors deeper drawing operation. So, you can have a very deep cup and other things to be made, and also higher normal anisotropy will reduce the wrinkles which can form in shallow parts. So, these are some of the advantages. Now, in homogeneity, when you talk about it, see every material has some defect due to say variation in composition. It may be due to variation in the texture and it may be the variation in the thickness, okay. Or maybe internal defects are there, maybe gas porosities or pinhole porosities or some inclusion, all these things are there. So, the homogeneity is something which is which is only like you cannot quantify it, homogeneity. Okay. So, it is only and so quantification of homogeneity is very difficult. Only by visual observation or observation under a microscope you can say this is better homogeneous, or maybe through microscopic technique by X-ray elemental mapping and other things you can say it is homogeneous, better homogeneity is there. But there is no quantification for so that way it is very difficult characterization of homogeneity, but only thing is that you have to, and that varies from person to person who is doing the analysis. Now, the surface features, how good is your surface? The roughness, and for that purpose many times for metal deformation you may use lubricants also. Okay. So, this roughness and the lubricants both will affect the forming operation, and maybe you may have to conduct some special test to characterize this lubricants and roughness and what is its effect on the forming behavior. Okay. And because the major thing is that this information is you cannot get it from a simple tensile test, because if you are doing a bulge test, it is like the tensile test result will not give you an idea about the what is the friction between the workpiece and the die. Okay. So, those difficulties are there. Now, the damage at microstructural level also affect the deformation behavior or forming behavior of this thin sheet actually, because you will find that during the processing itself some materials might have resulted in some sort of damage inside itself, maybe at microstructural level or submicrostructural or submicron level during the plastic deformation, and these can be determined from the tensile test. So, how much is the damage which has come, okay? Because if there is any damage which is taking place, then okay, this will show, it will be reflected in your stress strain curve, it will be reflected in your work hardening behavior. If there any damage has come, then you will see that there is a drop in the load. So, that way you can have an idea about what is the, how much is the damage which has already set in inside the material during the previous forming operation. So, but if there is a damage, then that also will affect your forming behavior, sheet metal forming, because sometimes in some case this defect which has already been nucleated, it may start growing, and then you may not be able to get extensive deformation of your component. The next is the rate sensitivity, that is the strain rate sensitivity of the material. So, this if you look at the strain rate sensitivity, you will find that these are very low at room temperature. See, strain rate sensitivity comes, it will be dominating at a higher temperature, not at lower temperature. So, at lower temperature it is almost, we can say, very low. Now, positive rate sensitivity can be positive or negative. So, positive rate sensitivity enhances forming and strain hardening. Okay. And effect of M, this is that M can also be evaluated by amount of extension in the specimen after maximum load and before rupture. Okay. So, that we can find out this rate sensitivity from the simple tensile test also. But many times that simple tensile test is most common test, but it does not provide all the properties. Hence, special tests are also required many times. What are these special tests? There are some spring back tests to find out the spring back effect. Then you may have to have a hardness test. In steels, this hardness can be correlated to your yield strength also. Then hydrostatic bulging test, so that you will have an idea about how much is the amount of metal forming it can take. And another is the simulative test. So, the spring back test is the measurement of spring back, and it is not possible in a tensile test. So, a series of spring back tests has to be done, like you will be just it is bent over a former. So, at certain angle you bend it and then release it and find out how much it is a spring back. So, plastically you deform it. Because of spring back, it will just unwind by a small distance. So, the sheet metal, it will be wound around a former, and you are allowing that while winding it undergoes some plastic deformation. And now the thing is that you release it, you will find that it is unwinding by some certain angle. So, this is the spring back effect. And then depending upon the thickness of the sheet, there is a limit up to which you can bend it. Once you bend it, okay, without so that before that defect sets in, and what is the maximum angle up to which you can bend without causing any deformation, and then once you release it, how much it unbends. Okay. So, that is what the spring back effect. So, for this you may have to work out with a large number of samples. Now, hardness is something which is the resistance of the material to indentation, and either the indenter can be a hardened ball or it can be a diamond pyramid, depending upon what type of hardness test you wanted to do it. So, and this can be easily evaluated. Okay. And the thing is that the smaller the indentation, when you are indenting with an indenter on your workpiece material, if the material is harder, the impression which it has made on the surface will be smaller in size. Okay. But if the material is very soft, the indenter can easily penetrate into that and more, and so that you will find that you are having a larger indentation. Okay. So, that is the indication of that. And most of the steels, the yield strength can be correlated to the hardness, but which is generally not practiced with in non-ferrous materials. These are basically indicated in steels. People have carried out extensive work trying to correlate between the strength and the hardness of the steel. Maybe when you do some different heat treatments and you get different hardness, then based on that your strength also will change. So, that information is already available. Third is the hydrostatic bulging test. So, in the hydrostatic bulging test, so you are having a sheet metal and with a spherical indenter, now you are just pressing it on one direction, okay, and then so that from the center, so that now there will be a biaxial tension which is there in all directions on the sheet metal. Okay. So, the true stress strain curve under equal biaxial tension you will get it. So, this test for materials having little strain hardening and possible to attain stress strain data over a larger strain range. Okay. Now, let us come to this sheet deformation. So, before we discuss about the mechanics, let us just summarize the very basic fundamentals which we have discussed in our initial lectures and other things, but here why we are discussing is that here again is that some terminology difference will be there, and in sheet metal working they have a different terminology which is being followed, that is why we will have to do it. Okay. So, for that let us assume a simple tension test. Okay. And in a simple tension test, take the gauge length and do that. In sheet metal operation, one important thing is there. In sheet metal operation, you will find that the stress which is perpendicular to the sheet surface, that is very small, since it is very small, whereas the stresses are acting in other biaxial direction, but through thickness direction the stresses are very small in sheet metal forming operation. And since it is very small, we can peacefully neglect it. Okay. So, that we will assume that the normal stress or stress normal to the surface of the metal sheet is 0. That means, the sheet is forming, the deformation process is a plain stress deformation case. Okay. Whereas, those stresses can be assumed 0, there will be strains in all the 3 directions, strains will be there. Though thickness is less, but strains are going to be there, and you will find that thickness reduction is going to take place also because of this. So, in a tensile test, if you take the gauge section, suppose let us take the tensile test specimen for a sheet metal, that will be a flat specimen, and you take the gauge section, how it will be? The gauge section will look like this. You have to draw it if it is like this, and let us have the principal planes on principal directions. So, let us say 1, 2, 3. This is the one direction. The direction 1 is the one having the highest stress, that will be your tensile axis itself. Okay. So, in that process, let us say that the material has just deformed by a small amount. Okay. Let us assume that the material has just deformed. I am just drawing it in an exaggerated way. Okay. So, that this will be, so if I just say that this is your length direction and this is your width direction and this is your thickness direction. Okay. So, you will find that okay, there is a small difference in this one, what is called along the width, length has increased. So, this is your dW. Okay. And maybe you may find that okay, since it is coming here, see this a small distance it is coming, which is your dt, maybe. And this is your delta L dl. So, dimensions has changed. So, let us assume that this is the direction 1, this is the direction 2 and this is your direction 3. So, this is 1, 2, 3. So, with respect to this coordinate system we can assume that in this. So, the principal strain increment in all the directions are, say, let us say principal strain increment so d epsilon 1 along the direction 1, it will be d L by L, okay, and d W, not delta, it is d, okay. D epsilon 2 is equal to d W by W, d epsilon 3 is equal to d T by T. This is the basic definition of this. So, if you assume the constant volume relationship, okay, maybe like initially, so that means d of L W T, if it is remaining constant. So, this is equal to, if you just take it as at any instant, and which is equal to, say, the initial value L 0, W 0, T 0, if you just take that. So, you can just expand it and then you will find that d L into W T plus d W into L T plus d T into L W. So, that will be equal to 0. So, that is the basic assumption which is taking place. Now, in all these things, if you just divide it by L W T, so we can say that d, it will lead to d L by L plus d W by L plus d T, d W by W, d T by T is equal to 0. The right hand side is 0 because this is a constant initial value, and left hand side also will be there, but values strain will be different. So, total strain will have to be equal to 0. So, constant volume relationship says, so that means under constant volume relationship leads to, because d L by L is d epsilon 1. So, strain increment along direction 1 plus d epsilon 2 plus d epsilon 3 is equal to 0. This is your the strain increments along the 3 mutually perpendicular directions, the sum of the strain increment will be equal to 0. So, that is the constant volume relationship. And when we come to this stress and strain ratios, because it is always you will find that for isotropic material, the properties in isotropic material, the properties are identical in all directions. Okay. So, in isotropic material, properties are same along all directions. So, considering this, no strain in the width and thickness direction will be of equal magnitude. Okay. So, that means if you just take it as so d epsilon 1 plus d epsilon 2 plus d epsilon 3 is equal to 0. So, the strain and thickness direction, the strain will be strain increments will be same. So, that means d epsilon 1 is equal to d L by L, and d epsilon 2 is equal to minus half d epsilon 1 and d epsilon 3 is equal to minus half d epsilon 1. Okay. So, this is because you are having a strain along the direction 1, then the sum of the strain in the other two will be equal to that is d epsilon 1 is equal to minus of d epsilon 2 plus d epsilon 3. Okay. So, and if this d epsilon 1 and d epsilon 2 are same, then you will find that okay, this is the case. D epsilon 1 is equal to. So, that way we will get this relationship. So, what are the stresses and strains? So, that means if you look at it, sigma 1 is equal to your P by A, where A is your cross sectional area, sigma 2 is equal to 0 and sigma 3 is equal to 0. I am telling this is for the tensile test. Okay. Okay. For a tensile test. For a uniaxial tensile test, that is the condition. So, that means you will find that these are the conditions. So, if you integrate this equation d epsilon 1, d epsilon 2 and d epsilon 2, you will always get epsilon 1 is equal to log L by L naught. Okay. Epsilon 2 is equal to log W by W naught, and that is equal to minus half epsilon 1. Similarly, epsilon 3 is equal to log T by T naught, that is also equal to minus half epsilon 1. Because for a uniaxial tensile test, we are assuming the stresses are only along one direction, the stresses at the other two directions are 0. That is why you have some geometric constraint to have a uniaxial tensile test. Okay. So, and if at all stresses are there, those will be equal also. So, maybe I can write that since this is because since the two principal stresses are 0. So, in actual in typical sheet metal processing, most elements will deform under the membrane stresses sigma 1 and sigma 2, because that is will not be equal to your uniaxial tensile test. Okay. So, in typical sheet process, in sheet forming, elements will deform under sigma 1 and sigma 2, and sigma 3 is we can assume it is a 0. Okay. Along the normal direction we have earlier mentioned, it is almost 0, because it is only negligible, we can just So, under this condition, for a sheet metal forming, you have sigma 1 and sigma 2. So, the conditions of sheet metal processing will be like of a plane stress deformation. Hence, most of the sheet metal process are plane stress deformation. Whereas, bulk deformation we always go for plane strain conditions. Okay. Here it is plane stress condition. And it is always convenient. It is convenient for deformation of the element under sheet metal processing to describe in terms of strain ratio and stress ratio. So, let us see what is that. So, because it has its own advantages, it becomes very convenient and become very simple for all calculations, stress and strain ratios. So, the stress ratio alpha is because you have only two stresses. So, alpha is equal to is defined as alpha is equal to sigma 2 by sigma 1. Remember, sigma 1 in all our cases, henceforth whatever we are discussing, sigma 1 will be the direction along with the highest tensile stresses are there. Sigma 2 can be either tensile or it can be compressive. Okay. But we are always taking that highest stress in the positive direction, that is the tensile stress, as sigma 1. Okay. And then this is the strain ratio is defined as epsilon 2 by epsilon 1. When a sheet is subjected to deformation, what are the stresses along these two directions? That ratio gives you the stress ratio, and the strain which is taking place in these two directions are the strain ratios. Okay. So, that means we can always say that in strain ratio, no, when it is along the direction 1 sigma 1, if it is there, what are the other strains? Epsilon 2 is equal to beta into epsilon 1, and if you substitute beta into epsilon 1, and if you substitute that, epsilon 3 will be equal to 1 minus of 1 minus beta into epsilon 1, because you substitute this, you will get it, the strain condition, and you have this sigma 1 is there, and your sigma 2 will be equal to alpha into sigma 1, and sigma 3 in the third direction, the normal to a surface, that is 0. You will find that for uniaxial tension test, from this you can always find it out, beta is equal to 0.5 and alpha is equal to 0, because sigma 2 by sigma 1 we are taking. Okay. So, for uniaxial tension, sigma 2 is equal to 0, sigma 3 is also equal to 0. So, that is why if you substitute that, you can directly get this. And next we will come to the maximum shear stress. Let us find out what is this maximum shear stress. See, if you just take a cuboid like this, or any, and you look at the general state of stress, if you just assume that on this planes, on the planes of this cube, there is no shear stresses, only normal stresses are acting. Okay. So, along this direction sigma 1, and this is along sigma 2, and this is sigma 3. So, along the on the face of the cube of the element, this is a principal element, tau is equal to 0. Okay. So, that means shear stress. But if you consider a plane even slightly inclined to that any of the faces, you will find that on those planes there is both your normal stress as well as shear stresses are acting into the picture. Okay. And with more and more inclination, you will find that the shear stress keeps on increasing, and a stage will come when the shear stress is maximum. Okay. So, that shear stress planes are inclined at 45 degree to the principal direction. So, for example, if I just take this case for illustration, this is sigma 1, sigma 2 and sigma 3. The shear stress by the maximum shear stresses, if these are the principal stresses, if sigma 1, sigma 2 and sigma 3 are principal stresses, if they are the principal stresses, then the maximum shear stress are given by So, you can get say different corresponding to the one plane, you just tilt that plane and see and keeping the other two parallel to other two, then you can find out what is this planes. Okay. So, we can get this tau 1 is equal to sigma 1 minus sigma 2 by 2, tau 2 is equal to sigma 2 minus sigma 3 by 2, and tau the shear stress. So, 3, this is equal to sigma 3 minus sigma 1 by 2. So, that way we can get it. So, for example, if you look at what are those planes, say if this is one plane, maybe okay, I have just, it is not equal to size. So, this part along with this directions, if you look at it, this plane, okay, in this plane you have this tau here. So, in this case now you will find that tau 1 is equal to sigma 1 minus sigma 2 by 2, the maximum. Okay, the sigma 2 and sigma. So, this will be, you will find that it is equally inclined to your sigma 1 and sigma 2. See, sigma 1 direction, see this direction, it is equally inclined to, this is the one direction, okay, direction 1, and this is the direction 2. So, with it will be equally inclined to the 1 and 2 and parallel to that. So, this is the direction of this maximum shear stress. Now, if you look at the tau 2, okay, so it will be this plane. Okay. So, and the direction will be along this, it can be this way or the reverse. Okay. So, this is your tau 2, the maximum shear stress in this particular plane. So, that is given by sigma 2 minus sigma 3 by 3, and you will find that it is inclined at 45 degree to sigma 2 and sigma 3, okay, along the 2 and the 3 direction. So, because this is 3, if this is 3, 2 and 3. So, it will be equally inclined to 2 and 3, and similarly you will find the next one as the maximum shear stress tau 3 along another plane. So, this will be equal to, say, maybe we can say this direction. So, this is tau 3 is equal to sigma 3 minus sigma 1 by, sorry, this is 2, not 3. By 2, and you will find that this plane, in this plane, so it is equally inclined to sigma 3 or direction 3 and direction 1, and this will be the direction at which the maximum shear stress will be acting in these two things. And you can always find out that from the and it is very easy to calculate this from the your what is called a Mohr circle. Mohr circle representation, if you look at it, it becomes very convenient. So, suppose you are having this here and you are having here, and this is your tau direction. So, you can draw this bigger circle, it looks like an ellipse now, maybe, okay, assume that, okay, it is a circle, it's something like this. So, this will be your tau 2, tau 3, because here this one is your sigma 1, okay. This is your sigma 2, and this the diameter of this A, it is equal to sigma 1 minus sigma 2. So, your maximum tau will be this one. So, what is that, tau 1, and this is tau 3 and this is tau 2. So, you will find that the maximum shear stress tau 1 is equal to sigma 1 minus sigma 1 plus sigma 2 by 2. So, that is what you are getting. So, all the three you can get it by your Mohr circle, this one. Now, when you go to that, the stresses at any point when you look at it, earlier also we have discussed there is a hydrostatic stress which is coming into picture, which is defined by your sigma h. In some cases it may be sigma m, okay, that will be based on the principal stresses, it will be sigma 1 plus sigma 2 plus sigma 3 by 3. Okay. So, where this is the sigma h is the or sigma m is the mean or hydrostatic stress. We will, since it is hydrostatic, we will use, sometimes it is used as a sigma m also, hydrostatic stress. See, the hydrostatic stress means it is of equal dimension, it is acting in all directions. So, like as if you have kept something inside of water and the fluid pressure is there. So, along all the directions this will be under equal this one, that is something similar to a pressure, but here it is only what is induced inside that. So, that is what stress at any point you can just consider that, and then the along the three principal, say the principal stress state can be written as a combination of the hydrostatic and deviatoric stress. Okay. So, for example, if I just say that okay, this is sigma 1, which I think this slide has been shown earlier also. So, if this is sigma 1, this is sigma 2 and this is sigma 3. So, this we can write as a sum of in all the three directions. Hydrostatic stress will remain the same. So, that will be a deviatoric stress say for example, sigma 2 dash, sigma 1 dash and sigma 3 dash plus a hydrostatic component, that means equal in all directions. Sigma h, sigma h, sigma h. So, that way along sigma 1, if you just look at it, sigma 1, the principal stress sigma 1 is the sum of a deviatoric stress sigma 1 dash plus the hydrostatic component. Similarly, sigma 2, if you take sigma 2 is equal to sigma 2 dash plus the hydrostatic component. Similarly, sigma 3 is the deviatoric stress along the direction 3 and the hydrostatic stress. So, along the three mutually perpendicular directions you are getting it. So, we can say the deviatoric stress is also called as the reduced stress or reduced stress. Why reduced stress? Because from your from all the three principal stresses you are just removing the hydrostatic stress, which is an equal value about that. So, that we can say we can write the sigma 1 dash is equal to sigma 1 minus sigma h. Similarly, sigma 2 dash is equal to sigma 2 minus sigma h and sigma 3 dash is equal to sigma 3 minus sigma h. So, that way we can just write like this along the three directions, but if you are writing this substituting the value of sigma 1 plus sigma 2 plus sigma 3 and say if you say sigma 2 is equal to alpha sigma 1. So, if you are using this sigma 2 is equal to alpha into sigma 1 and you substitute under these conditions in a similar way, you can write that sigma 1 dash in terms of alpha. If you can write it as 2 minus alpha by 3 into sigma 1, you just substitute in this sigma h is equal to plus sigma 1 plus sigma 2 plus sigma 3 by 3 and then you do it, you will get it. Similarly, sigma 2 dash you will get it as it is equal to 2 alpha minus 1 by 3 into sigma 1, because you can easily measure the sigma 1 and then okay, sigma 3 dash is equal to minus of 1 plus alpha by 3 into sigma 1. So, basically the deviatoric stresses are the difference between the actual the principal stresses and its hydrostatic stress. So, that is what. So, now let us look at these conditions and apply this on your yield criteria, because these are the relationship between the stress and strains. Now, we have to, using this relationship, we have to look into the yield criteria. So, let us say first is the Tresca criteria. So, in the Tresca criteria, if you say a uniaxial state of stress in sigma 2 is equal to sigma 3 is equal to 0, maximum shear stress at yielding is equal to your flow stress. So, that means for a, you have to find out which is the greatest maximum shear stress. So, Tresca criteria says that yielding of the material will take place when, because you have three maximum shear stresses. The greatest of the maximum shear stress, when it reaches a critical value, yielding will take place. Okay. So, yielding or plastic deformation will take place when the greatest maximum shear stress reaches a critical value. And what is this critical value? You have to find out. The simplest thing for finding out the correlating is to get a tensile test. That is because you can always correlate it and correlate with that one. So, in a tensile test, since sigma 2 is equal to sigma 3 is equal to 0, then the maximum shear stress is tau max is equal to sigma 1 minus sigma 2 by 2, where sigma 2. So, this is 0. So, that means it is equal to sigma 1 by 2. So, that means in a uniaxial tensile strength you are conducting, what is the yield strength you are getting. So, that is that. So, this we can write that this is equal to say sigma 0 by 2 is a uniaxial, where sigma 0 is the uniaxial yield strength of the material. Okay. So, the Tresca's yield criteria will occur as per Tresca's criteria. Yielding will occur when sigma max minus sigma 2 by 2 is equal to sigma 0, or we can say the absolute value of sigma max minus sigma minimum is equal to sigma 0. So, under plane strain condition, the plane strain yield criteria, the Tresca's criteria for yielding under plane stress, it will be a hexagon. Okay. So, that if you just plot it like this is sigma 2, sigma 1. So, this is your sigma f and this equal to your sigma f. So, we can just say that it comes like this, and from maybe here it comes, okay, and so this will come down and it will reach here, and this is your hexagon. So, you will find that this is sigma f or sigma o, and this is equal to sigma O. So, this is minus sigma O, and so similarly. So, it looks like a hexagon. So, if you look at under all these conditions sigma 1 and sigma 2, if you just take all these conditions, you will find the locus of that point is a hexagon. Okay. That indicates the state of stress as the stress ratio changes. So, when stress ratio changes, how it goes. Now, when the material is work hardening, this hexagon it will expand outwardly, because your flow stress sigma 0, that will keep on changing accordingly. So, it may come like this here, and it may go like this. So, when the deformation is taking place, you may find that, but still it will be a hexagon in the same shape. Okay. So, this first the straight line which has been drawn is for a fully annealed material when you are just deforming it. Okay. But when the deformation is changing, and if you are maintaining the stress ratio constant, then you will find that okay, this the hexagon size keeps on increasing, because your new sigma naught flow stress will come into picture. So, now let us look at the von Mises criteria. According to the von Mises criteria, earlier we have discussed in depth for bulk deformation process. So, because these, I am again telling this because the terminology used in sheet metal forming is different. That is why we have to always represent in terms of stress ratio and strain ratios. That is why it is coming. So, yielding will occur when the root mean square value of maximum shear stresses reaches a critical. Occur when the root mean square values of maximum shear stress reaches a critical value. So, what is that critical value you have to find out. So, for that now at when you are doing a tensile testing, during the at yielding, two of the maximum shear stresses will have a value sigma f and the third one is 0. Okay. So, in a sheet metal work. So, in a tensile testing. So, the criteria here what we have mentioned, we can explain it in this way, that is tau 1 square plus tau 2 square plus tau 3 square by 3 is, we can say, is equal to sigma f by 2 the whole square by 3. Why? Because sigma 1 and sigma 2 is equal to minus of this value. So, that way, so two values which will be there, it will be the your uniaxial flow stress by 2, that is what is going to happen. So, this is what you are going to get it, or we can also write. So, in this condition, so root of 2 into tau 1 square plus tau 2 square plus tau 3 square is equal to sigma f, sigma naught, uniaxial flow stress of the material. Okay. So, this is one advantage. If you have conduct a uniaxial flow stress, you can just correlate with this value, what is the von Mises criteria and Tresca criteria, that is one advantage with this. And if you use this for tau 1, tau 2, tau 3, you know, if you are using your say where tau 1 is equal to sigma 1 minus sigma 2 by 2, okay, and tau 2 is equal to sigma 2 minus sigma 3 by 2, and tau 3 is equal to sigma 3 minus sigma 1 by 2. If you substitute in this, no, you will get this is equal to root of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square So, that is equal to, because this 2 will come here. So, it will be root of 2 sigma 0. So, this is what you are going to get, because here all this 2 is coming below. So, that is why it will, you will come to this. So, if you just substituting in terms of deviatoric stresses, you will say that sigma 1 dash is equal to 2 minus alpha by 3 into sigma 1, and sigma 2 dash is equal to 2 alpha minus 1 by 3 into sigma 1, and sigma 3 dash is equal to minus of 1 plus alpha by 3, which we got it earlier, into sigma 1, and sigma 1 dash is equal to 2 sigma 1 minus sigma 2 minus sigma 3 by 3. We are getting, you for the plane stress, the criteria is, for plane stress, the von Mises criteria comes to sigma 1 square minus sigma 1 sigma 2 minus sigma 2 square. So, that is equal to, you will get it as 1 minus alpha plus alpha square into sigma 1, that is equal to sigma 0. So, this is your von Mises. So, both these expressions are valid for isotropic materials. So, if you look at the von Mises criteria, how the yield locus look like. So, that also we have discussed earlier, but let us just revise it here. So, this is your sigma 2 and this is your sigma 1. So, it will be an ellipse, okay, somewhere like this it will go. Okay. So, this is your, in all the 2 directions, if you take it, you will find that this is your sigma 1, sorry, sigma f, or uniaxial flow stress sigma naught, and this will be your uniaxial flow stress. Okay. So, it will look like this, and this is a case for alpha is equal to 1, somewhere here at 45 degree. If you look at it, this is equal to alpha is equal to 1. Okay. So, this is the condition you can always take at any point on the strain history. If you look at it, or you can find out what is the criteria for yielding at this which is taking place. Now, when the material is work hardening, you are say plastically deforming it, this will again expand, but the shape will still remain the same. Okay. So, so yield criteria helps to predict the stresses at which a plastic deformation occurs in plane stress condition, where the ratio of stress in plane of the sheet to flow stress of the material, if it is known. So, it will be able to predict the stresses. In elastic deformation region, see whatever is inside this ellipse is the elastic deformation region. Stress and strains are directly related and can be calculated very easily, because it follows the Hooke's law and other things. So, it is very easy to find out in direct relationships you get it. But the thing is that when you come to plastic deformation region, there is no relation which exists, and it may happen that at some stage material may be under the state of stress, but there is no change in the shape. That also it can happen. So, magnitude of deformation depend upon the boundary movement and not on the stresses. So, that is the thing which happens. Now, let us come to say Lévy-Mises. In plasticity, this we have to, this is very important, Lévy-Mises flow rule, which also we have discussed, but still now it is time that we have to look at it, because we have already discussed the actual state of stress, actual stress state in a material is a combination of the hydrostatic and the deviatoric state of stress. In that, the hydrostatic stress will not influence the shape change of the component. Okay. It will just tell maybe its volume increases or decreases, but shape change is not being caused due to hydrostatic stress. Only the size of the component only will change due to effect of the because equally in all directions it is coming. Whereas, what causes the change in the alters the stress state or sorry shape of the component is your deviatoric stress. So, this Lévi-Mises rule states that the ratio of strain increments will be the same as the ratio of the deviatoric stress. So, the ratio of the strain increments will be the same as the ratio of deviatoric stresses. So, that means strain in say for example, strain increment d epsilon 1 by sigma 1 dash is equal to d epsilon 2 divided by on the deviatoric stress in that direction, that is equal to d epsilon 3 into sigma 3 dash. So, in terms of your if you write that sigma 1, sigma 2, sigma 3 in terms of your alpha value, the stress ratio, we can write this as d sigma 1 divided by 2 minus epsilon is equal to d 2 minus alpha d sigma 2 divided by 2 alpha minus 1, that is equal to minus of d epsilon 2 divided by 1 plus alpha. We can write in this term in terms of alpha. Okay. And see the under plane stress condition, what happened the proportional conditions, if it is deforming under proportional condition in all directions, the stress ratio, that means the stress ratio is maintained a constant, then we can integrate this above equation and to get the strain itself, okay, instead of strain increment. So, this one by 2 minus alpha is equal to epsilon 2 by 2 alpha minus 1 is equal to this is equal to beta epsilon 1 by 2 alpha minus 1, because epsilon 2 is equal to beta into epsilon 1 is equal to epsilon 3 by minus of 1 plus alpha. So, that is also equal to, you can write in terms of epsilon 3 as, see this one 1 plus in strain increment, if you write it as epsilon 1 by minus of 1 plus alpha. So, we can write the Lévi-Mises rule follows this one, but this we were discussing about the stress ratio and the strain ratio. These are correlated. The relationship between alpha and beta, that we can correlate, that is alpha is equal to 2 beta plus 1 by 2 plus beta, or we can write it as beta is equal to 2 alpha minus 1 by 2 minus alpha. This way also we can write. But this relationship between the stress and the strain, it will not give the exact value of the strain, that is true. Okay. It is only we can correlate with it, it will not give you the exact value of this thing. So, if you look at the flow rule, Lévi-Mises flow rule, it gives the relationship between the stress and the strain ratios. It will not indicate the magnitude of the strain. So, that is one thing. It will not tell you the exact value of the strain. If the element deforms under a given stress state, or if alpha is known, the ratio of the strain in the previous case and this case, that we can find out from along the two directions. but it will not give an absolute value. So, initially if you know the value and then okay, under a constant alpha it is moving, it is deforming, then we can have the strain, that is all. So, the relationship can be illustrated for different load paths as shown here in the, if you just take this, this is your sigma 2 and d epsilon 2, this is your sigma 1 and the same direction. So, if that way if you do that, then so you can just get that. If I just draw this, this is the case where d epsilon 2 is equal to d epsilon 1. Okay. So, this slope is 1 and 1, and this is a case where you have half, slope is half, and then maybe you can just from here you can just draw it as d epsilon 2 is equal to 0, and this is d epsilon 2, d epsilon 2 is equal to minus d epsilon 1 by 2. So, if I just draw like this, sorry, so this is the condition when d epsilon 2 is equal to minus d epsilon 1, and here it is minus 1 and 1. So, these are the conditions which we are getting. It will look like this. Now, when we discuss about this deformation, it is very convenient to express the stresses as effective stress and strain as effective strain, because earlier also we discussed the say for example, effective stress and strains. Okay. The plastic work per unit volume, if you just calculate it, it is dW this plastic work, dW by whatever volume is there, it was expressed on sigma plus d epsilon 1 plus sigma 2 into d epsilon 2 plus sigma 3 into d epsilon 3. So, this we can always write it as a two function, a function of maybe sigma 1 the principal plane, sigma principal stresses, sigma 2 and sigma 3, and maybe another, so if I just write this as f 1, another function into another function which is nothing but your epsilon 1, epsilon 2 and epsilon 3. We can write like this. So, this is a stress function, and this we can call it as a strain function. So, this total plastic work per unit volume we can write in terms of a stress function multiplied by a strain function. So, that is what we can write. So, the stress function is called called the effective or equivalent stress. So, that is we can say that f of principal stress sigma 1, sigma 2, sigma 3, we can write it as sigma bar, which is the effective stress. So, we can write as in terms of your von Mises criteria, that is sigma 1 minus sigma 2 square plus this sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square we can get it. So, for plane strain condition, plane stress condition, because in sheet metal we are using the plane stress condition. So, for plane stress condition we can substitute that condition for sigma 1, sigma 2, sigma 3 and other thing in terms of sigma 1 and sigma 2. So, that the effective stress we can say sigma bar is we can write it as root of 1 minus alpha plus alpha square into sigma 1. So, that is what we can get it. Similarly, the strain function, representative strain function sigma 2 in terms of epsilon 1, epsilon 2, epsilon 3, we can write it as for plane strain condition we can write. So, this is equal to d epsilon bar. So, that we can write in the form as 4 into 1 plus beta square by 3. We can write it in this form. Why? The general state of stress, now if you look at it, it is d epsilon bar is equal to, for the general state, if you just 2 by 3 into, it is equal to d epsilon 1 square plus d epsilon 2 square plus d epsilon 3 square. Okay. So, that is which is nothing but you can always write it as 2 by 9 into d epsilon 1 minus d epsilon 2 the whole square plus d epsilon 2 minus d epsilon 3 the whole square plus d epsilon 3 minus d epsilon 1 the whole square. So, in this way we can write it. So, if this is going on a proportional process, the equivalent strain increment. So, if it is on a proportional process where the alpha and beta remains constant, in that case from the so this above equation can be integrated from the natural or true strains and substituted to incremental strain. So, we can get it as you integrate it, you will get it as like this. So, 2 by 3 into epsilon 1 square plus epsilon 2 square plus epsilon 3 square. So, that is equal to, you can write say 2 by 9 into, so that is what we are getting this. Okay. So, the same thing, when you are integrating you will get it as 2 by 9 into epsilon 1 minus epsilon 2 square plus epsilon 2 minus epsilon 1 square plus epsilon 2 minus epsilon 3, epsilon 3 minus epsilon 1 square. We will get it in that form. So, it is always convenient to represent in terms of equivalent strain and equivalent stress. This is, and that relationship for equivalent strain we can get it as here, and for the equivalent stress we can or effective or equivalent stress we can get it as this. This is sigma 1. Okay.